Hello there, exercise 6a for further maths. This is a pure core 1 topic, year 12. And we do come back to it again in year 13. But this is definitely a new type of proof, a new type of way to go about proving an idea it's not an obvious way to do it. But somewhere along the line has thought, I know what to do, effectively you need to learn this process, and we're going to do it today with matrices. But in due course, we'll also do it with other types of proof using mathematical induction. So here goes. So 4 steps to mathematical induction, then we're just going to use this 4-step process on all of these. Number 1 is to check that the proof, the theorem that you're being asked to prove works at least in one case, and usually you do it for n equals 1. Step 2, you assume it's true, this theorem that you are being asked to prove, you assume it's true and you write it out for n equals k. Step 3, you prove it. This is what's often called the iterative step. You prove it for n equals k plus 1, and then you write out what we call a completion statement, and all of that should probably completely confuse you. But nevertheless, write it all out, and then you'll see this in action in a bit. You might need to pause the video just so that you can write all that out, but definitely I'd write it all out. And then this completion statement that we're going to learn off by heart, there's other versions of it. This is the one that I always get my students to write. And it's simply because, that's what I've seen on the past exam paper on the model answers. So the exam board said they should write this, and although I'm sure they accepted other versions, this is what I've said ever since then I've written out. So this would be my first example for you to see. So I quite like this in as much as it's slightly structured for us. It says the matrix is given by A equals 2, 0, 0, 1. And it actually wants us to find a suitable like a formula for a to the n. Now obviously a to the n is where you multiply it multiple times, multiply it by itself lots of times. So let's just go about doing this. Okay, so here's my pen. So a equals 2, 0, 0, 1. Obviously I have to find a squared, and there's nothing wrong with us doing it on our calculator. So I'm just going to go 2, 0, 0, 1. Squared, obviously, and we can do that in a variety of ways. And I'll also need to do a cubed is 2, 0, 0, 1 cubed. And I suppose we're just going to type those in. I'm going to pause my video now and just type them into my calculator. And these were my answers. So I've typed them in, and so a squared becomes 4, 0, 0, 1, and a cubed becomes 8, 0, 0, 1. So immediately, having got these two answers correctly here, and notice it doesn't say show how you found your work, and that just says fine. So that's fine. I'm allowed to just type them in. But the bit I'm really interested in is hence suggest a suitable form of the matrix A to n. I want to know what a to the 4 is equal to. I want to know what a to the 5 is equal to. And I suppose ultimately I want to know what a to the 6 is equal to. Not a to the 6, a to the n is equal to. So on that basis that I'm going to try and find this formula a to the n, let's just have a look at it. Now remember this is I suppose a to the 1, and it's 2, 0, 0, 1. Then a squared is 4, 0, 0, 1. And it just looks like these numbers, the next one's 8, these numbers are just powers of 2. 0, 0, 0, 1 is obviously going to be 0, 0, there, 0, 0, 1 I meant. That's going to be as it is, but these ones, isn't it? A to the 1 is a 2, so that just says 2 to the 1. That's 8, that's 2 to the 2, that's 2. This is just 2 to the n. This is quite easy. So that's what I think the formula is. And of course, it's one thing to think it, it's another thing to know it. And the way we prove it is we're going to use proof by induction. So let's just go back to our initial rules. We got these 4 rules, 4 steps that we're going to follow each time. Step 1, step 2, step 3, step 4. I'm just going to remind you of these as I go through this proof. So step 1, I'm going to always write 1. I'm going to say check my rule for n equals 1. And actually I've kind of already done this, because if I put this in here, I get a to the 1, and it's equal to obviously 2 to the 1, 0, 0, 1, and 2 to the 1 is 2, 2, 0, 0, 1, and this is what it was. This is what they told me it was. So this I've kind of can say it's true for n equals 1. And that, believe it or not, is first step done. Second step is actually even easier. It says assume my rule is true. And a bit weirdly, I always switch the letters. Assume for n equals k. Now that's a bit of a pedantic reason for doing it, but just get into the habit of doing this. Basically, my rule, I think, is here, a to the n equals this. So I can write a to the k equals 2 to the k, 0, 0, 1. And that's definitely a 2 to the k. Let me just get my rubber here, because I just want to make sure that's very obviously a 2 to the power of k. There, that looks better. So I've now done my first two steps. Now this step 3 is the tricky step. This is where we're going to prove for n equals k plus 1. And to do this, what I have to do is I go back to thinking, well, what is a to the k plus 1? And it's obviously equal to a to the k times by a. Well, I suppose technically a to the 1. So on that basis, I can say a to the k plus 1 is equal to, well, you see, this a to the k, I now know what it is. Well, I've assumed I know what it is. And essentially then I can write 2 to the k, 0, 0, 1. And I'm going to times that by 2, 0, 0, 1, because this is what the a to the 1 is. The a to the 1 was given me right at the start. And so now I've just got to do a bit of multiplication. I've got to use my matrix multiplication rules. It's 2 to the k times 2. Well, that is 2 to the k plus 1. And then I have to add on 0 times 1 is 0, so I can ignore that. 0 times, 2 to the k times 0 is 0, and 0 times 1 is 0, so that's worked. 0 times 2 is 0, 1 times 0 is 0. This is all working out very nicely. 0 times 0 is 0, 1 times 1 is 1, that is 1. Now the key here is that's what I expected it to be. So this is the given result, if you like. This is the result I wanted. And this is where step 4 comes into play. This is, I could write something like here, as required. And step 4 then basically is me writing out this completion statement. I would literally write out, this is the given result with k plus 1 replacing k. Therefore, if it is true for n equals k, it must be true for n equals k plus 1. Since it is true for n equals 1, it must be true for all positive integers. And this is basically the idea. The idea is that we assume it's equal to n equals k. We prove it's equal to n equals k plus 1, which is fine. So if this is true, then this is also true. Now, we've already proven it's true for n equals 1. So that means by this rule, it's true for n equals 2. So we know that. Oh, hang on a bit. If it's true for n equals 2, it's true for n equals 3. Oh, hang on a minute. If it's true for n equals 4, it must be true for n equals 4. And 3 is 4. And you just keep on going on this logic. And basically, you end up at infinity very quickly, because this rule says it will always work for one more than the one you're on now. That's what's going on. But I've got to stress, you need to write out this statement. This is the given result, etc. And I'm not going to do it, but I want you to do it, because you'll be expected to do it in your exam. Let's have a look at another example of this. Now, example number 1 then. This looks very, very similar, in fact. Let's just have another go at this then. So find m squared and m cubed. Well, based on that, I'm going to pause the video and I'm going to work those out again. And this was a bit of a surprise, actually, because having seen the last example, I was expecting it to go 1401 and then 1801, and actually when I typed it in, I've ended up with 1601. So that was a bit of a surprise. I suppose it suggests, well, does it suggest? I don't know. It looks to me as if it suggests this as an m to the n formula, where I've got 1 and I've got the 0 and the 1, all very happy. But this 2, it's kind of gone double it, it's gone treble it, I think this goes 2n. This is not a power, this is just a straightforward times of my 2. So that's what I think the formula is. It seems reasonable, and it now says use induction to prove it. So number 1, let's do the same thing. I check for n equals 1. Now for n equals 1, using my formula, I'm fairly sure it will work because I made sure it did. It's 1. What do I need to do? I need to do 2 times 1, 0 and 1, which is obviously 1, 2, 0, 1, which is what I had. This is what I had, 1, 2, 0, 1. So I can just write true for n equals 1. So I've checked it, it works. Now number 2 is my assume. And whenever I do it, the mere fact I'm doing this now says perhaps you should always write this out as well. Make it crystal clear to the examiner what it is you're trying to do. And I'm going to assume this rule works for n equals k. And that basically just means repeating what I've written here, but with a new letter. And it says m to the k equals 1 2k 0 1. Number 3, this is always the tricky step, prove. So n equals k plus 1. Now, in all honesty, with matrices, it's not too tricky a step. When you do other proof by inductions with other types of formulae, it becomes trickier. But I've deliberately started with the matrices here because I think it's relatively straightforward. But just be aware, it's not always. So anyway, so how do I work out m to the k plus 1? Well, same as before. I say, well, that's equal to m to the k times by m to the 1. But I can add the formulae. And this gives me then, well, m to the k, what is it? It is what I've assumed there. It's 1, 2k, 0 and 1. And I times that by m to the 1, which I know is 1, 2, 0, 1. So let's just go through. Last time it's fairly obvious what happened. Let's see if it is here. 1 times 1 is, well, that's 1. And then 2k times 0 is, yeah, so if there's obvious working out, you should show it, but it might be not be. So 1 times 2 is 2. Here there is. 2k times 1 is there. Then 0 times the 1 is 0. 1 times 0, that's 0. 0 times 2 is 0. 1 times, that's 1. And I suppose at the moment it's not equal to what I want, but this is where I can just go, it's 1. And I can write here, a 2 comes out with a k plus 1. And you can see I factorised the 2's, the 0 and the 1 as before. And I suppose this is where you start realising what this completion statement number 4 means. And I would now write out this is the given result with k plus 1 replacing k. Can you see how here it said 1, 2k, 0, 1, and now it says 1, 2 lots of k plus 1. The k has been replaced with a k plus 1, which is what it says here. And then the rest of it, which you also must write out, guarantees that you are showing that you've got it right. But one more example to go through. So let's have a look at that. This is example number 2, and it says here, all right, now here's one where they're actually given us the formula. Now I'm assuming they're giving us the formula because it's just a more complicated formula. It's not one you'd necessarily think of yourself. But we go through the same process. Step 1, we check our formula. Particularly now, it's important because we didn't work this formula out for ourselves. Check for n equals 1. So I write a to the 1 equals 3 to the 1, a half of 3 to the 1 minus 1. And notice I'm showing my working out because I want to make sure I get all the marks. That's a 0, that's 1. And what's that give me? That gives me 3. Interesting, that's right. Now 3 to the 1, I'm doing the brackets first, is 3, minus 1 is 2. A half of that is 1. 0 and 1, true. So this is true for n equals 1. Tick. So I've done the first step. Number 2, I check. So this is I check. Oh, sorry. Let's rub that out. I'm going to assume for n equals k. And this is just the simple idea that you switch the letter. So I'm going to write a to the k equals. And then whenever I'm writing this, I always think, this is a bit of a waste of time. And it kind of is. But if that's what they want us to do, that's what we do. And there's that. And now, of course, I do the proof, the tricky iterative step. Now, step 3 then is the one where we prove that. So let's just write here, prove for n equals k plus 1. And oops, my pen's gone a bit haywire. And the way we do this is the same as before. We would basically use this trick that says a to the k plus 1 equals a to the k times by a to the 1. Little times in there, perhaps just make it clearer. And so what do I, now this is where I use my assumption that this is true. And definitely a bit more complicated this time because of all that brackets and the powers and stuff. And I'm going to times that by a to the 1, which was 3, 1, 0, 1. So if I just multiply these out, I get 3 to the k times 3 to the k, 3 to the 1. So that's like 3 to the k plus 1 plus, and this is where you've got to make sure you do it right, is this phrase times by 0. Oh, that's 0, so that's easy. I don't have to write that. 3 to the k times 1 plus this times by 1 as well. That times by that, and that times by that. Yeah, I've done that right. So that's a half of 3 to the k minus 1. Now you can see I'm going to do some work on that. 0 times by that, and 1 times by 0 will give me 0. And 0 times by 1, and 1, that will give me 1. So that, everything else is fine. But what I still need to do is just tidy this up. So it might take a bit of work. 3 to the k plus 1 I think is fine. You can see there the k plus 1 has just replaced the k. That's 0, which is the same as this one, 0. That's 1, that's fine. This is the tricky one. And I suppose if I multiply out that bracket, I get 3 to the k plus a half of 3 to the k minus, minus a half. And I've got to do a bit of work on that still. It's 3 to the k plus 1. No. Now, what does this give me? This gives me like 1.5. So I'm going to write that as 3 over 2 lots of 3 to the k minus a half. And here's the trick. Here's what I need to say here. I can say this is 3 to the k plus 1, 0. And I can take out half as a common factor, which of course is what I need to do. And that gives me 3 lots of 3 to the k. And if you just think about what I just said, I'm going to write 3 lots of 3 to the k. But that is like 3 to the 1 times 3 to the k. And of course that is 3 to the k plus 1. So although it doesn't initially look like it, I think that becomes 3 to the k plus 1. Obviously I've taken out a half, so I can write minus 1. And this definitely then is one of those as required. You can now write out your statement. This is the given result of k plus 1 replacing k, etc. And even if you're not convinced, if you just look at it after a while, this is the tricky step, I suppose, there to there. And this was my working out to justify it. This is something we need to be able to do. And it's this third step. This was a first proper look at an example where you think, oh, that was a bit more complicated than the others. Look, I've got an example for in class, but before I want to move on to that, just remember what we're going to do all the time. Step 3 is the tricky one. This is the rule that we use. M to the k plus 1 is m to the k times the m to the 1, I suppose. And that is the result, of course, that we used in step 2, or we assumed in step 2, and therefore it's relatively straightforward to do. And then it's just a case of, have you got the algebra skills, have you got the multiplication skills, matrices, to prove that it is what you hope it is. Don't forget your final step, your final step 4, you must write that out. And we're going to do a class example, and we'll worry about that in due course. And that's what we're going to do in class. We're going to do exercise 6A from the textbook. Thank you very much.